you just look at how many of the posterior samples are consistent with your restriction and how many of the prior samples are consistent with your restriction. And then the ratio of those two is your base factor. So to make this more clear, we're going to go over 3 examples. First, the inequality constraints. So very simple examples. Example, we have 2 parameters, say mu1 and mu2, and the null hypothesis. So in the alternative hypothesis here, these parameters mu1 and mu2 are free to vary, but here we have a restricted version in which mu1 is greater than mu2. So I'm going to show you pictures like this, and we assume here that the prior on these parameters is locally uniform. So I'm going to talk about 3 situations, A, B, and C, and these circles, they represent the posterior distribution. So the joint posterior. So in this particular case, the order restriction corresponds to the gray area, right? So the proportion of posterior samples consistent with the order restriction is 1/2. And then we are going to look at the proportion of posterior samples that is consistent with the order restriction. So in case A, that's also 1/2. So that means that we have no evidence either way. The base factor is 1. If we look at case C, almost all of the posterior mass is consistent with the order restriction. So that means that we have a proportion of almost 1 divided by 1/2. So our base factor is 2, which is or almost 2. So if you, in this particular case, if you get data that are perfectly consistent with your order restriction, the data are twice as likely to have occurred under the restricted model than under the full model. And in this particular case, you have almost no posterior samples that are consistent with the order restriction. So you have a number very close to 0 divided by 1/2. So you have quite a lot of evidence against the restriction. Now, we can also look at about equality constraints in this framework. And we simply say that mu1 is close to mu2. And we define some epsilon difference, maybe based on some substantive research, like a relevant difference. And we do the same thing. And pictorially, it looks like this. So the number of prior samples consistent with this restriction may be about, say, 1/10. And if you look at case B, for instance, almost 1/2 of the posterior samples are consistent with the restriction. So that means that we have a base factor of 5 in favor of the restriction. And that also holds in this case for case C. But now, we might wonder what happens if we make this epsilon very small. So, in the limit, when we make it very small, and if we stick to this pictorial representation, so we're going to look at this situation where epsilon gets very small, so we effectively want to test an exact equality constraint. We get this. So we need to calculate now the number of posterior samples that lie exactly on that line, divided by the number of prior samples that lie exactly on that line. And that is, in this case, because they're continuous parameters, it's 0 divided by 0. So some people have argued that in this particular framework, the end result is not defined. However, it is. And you can see this if we switch to a slightly different representation, where I'm not going to plot mu1 and mu2 separately, but I'm just going to plot the difference of them. Right? So I'm going to show you a prior and a posterior for the difference between these parameters. And that brings me to the second sticky density ratio test. I should explain the Savage-Dickey ratio test first, I guess. So these Savage and Dickey have shown that when the priors for the encompassing model are determined just as Helmholtz and Klutkis do, you have a base vector here, probability of the data given the null divided by probability of the data given the alternative, and then you get this. So delta, that's the difference between mu1 and mu2. So this is an exact equality constraint. And what this says is you look at the height of the posterior, and you divide it by the height of the prior at the point that you want to test. So it looks like this. So when we have an about equality constraint, and we use the encompassing prior approach, we basically we compare the area under the prior distribution, that's the solid line, the area under the prior distribution, and we compare it to the area under the posterior distribution. And now the question is, what happens if epsilon goes to 0? And it is straightforward to show using, well, you can actually already intuit this when you see it, but you can also show it very easily using the rule of L'Hopital, that what you end up when epsilon goes to 0 is just the ratio of these two densities. So I felt this was an interesting result. You can look at it in two ways. In one way, you can say, well, the Savage-Dickey test is a special case of the encompassing prior approach, or you could say, equivalently, the encompassing prior approach generalizes the Savage-Dickey test to hypotheses that have order constraints, so that aren't exact equalities. Good. However, if this was all there was to it, it would be too good to be true, of course. So there is a problem, and that problem is the Borel-Kolmogorov paradox. And it's such a nice paradox that I wanted to tell you a little bit about it. I hope you enjoy it. I certainly did. And that actually, this topic also attends me to the fact that I've been very egoistic here. I have not mentioned the contributions, the major contributions of Ruud Wetzels and Wolf Grassmann, my co-authors on this presentation. Okay. So the thing is that if you use this particular methodology for the exact equality constraints, you run into the Borel-Kolmogorov paradox. And to illustrate what this is, here's a unit square, and we have a point P that has a uniform distribution on this unit square. Now, given that P lies on the diagonal, what is the probability that it lies in this particular area A? Now, we need to condition here on something that has probability 0, because the probability that that point will lie exactly on that diagonal has probability 0. So in order to calculate the required conditional probability, we need to consider the limiting process here. So just to give you, there's multiple answers to this problem. I will consider two. So and the idea is like you need an idea of what it means to be on the diagonal. So in one conception of it, you can just say, well, x minus y is 0. And if you then plot epsilon, and you let epsilon go to 0, you can calculate the probability that you're in A, and it's 1/2, which is intuitive, I would say. But there's a different way of doing it. You can say, well, x divided by y equals 1. That's what it means to be on the diagonal. And then, if you let epsilon go to 0, the probability of being in A is 1/4, which is counterintuitive. But it's not wrong. It's just an alternative answer. So what this means for testing exact equality constraints using this framework is that your results, your base vector, depends on the parameter transformation that you use, or the parameterization that you use. So it's not unique. And this holds, for instance, when you test a parameter delta defined as mu1 minus mu2, and you put priors on mu1 and mu2. If you then start transforming mu1 and mu2, you run into this problem. However, luckily, if you put a prior on delta and you formulate your model like this, then you can transform delta all you want, and the result will be the same. It is not a solution to this deep paradox, but it is a way of sort of dealing with it. There's other ways. So, for instance, this was one way, one encompassing prior approach, one way to set your priors for the smaller model based on the larger model, but there are other ones that have been specifically designed to avoid this problem. Unfortunately, they introduce new problems of their own. So, there's advantages and disadvantages here. But it's certainly something to be aware of when you do this. And I think with that, I'll conclude my talk. Thank you very much.
Thanks for a nice presentation. We enjoyed the paragraph. Just conceptually, if you allow quality constraints to be concerned, why not also allow inequality constraints on the surface and then prior for it? And the second question is, there's now so many priors around. What about Bayesian evangelical Bayesian story?
Right. Well, then I think I'll certainly answer the second question first. There are a lot of priors, but actually in this framework, you can. The nice thing about it is that you can compare these models, and you of course need a lot of priors. For every parameter, you need a prior, but most of these priors are they won't affect the result. The main prior that will, of course, affect the result, and that's the crucial one, that would be this one. So you can see very clearly here that the impact of your prior, what the impact of your prior is on the base vector, because if you change your prior, you immediately change the height ratio, because your posterior won't be affected by the prior as much. So then the question is, what kind of prior should we choose? Now, this is a big conceptual challenge, right? But that conceptual challenge has always been there. What I try to address here is the computational challenge. Right, but I did not quite understand your first question, so maybe we should have another one.
What interpretation generic should we attach to mu1 and mu2? I didn't find the ratio equals 1 to be very plausible on that point when mu are location parameters, because you're not preserving the dimensional structure, whereas mu1 minus mu2 does. In fact, mu1 minus mu2 over sigma, the effect, is dimensionless, and that has no problems, and it still obeys. You can still write your equality hypothesis as that effect size equals 0.
All right. So that went very quickly for me. The way we're doing things now, and so I'm not sure whether you agree with this, but the way we're doing it now is we're using this mu2 equals mu1 plus this difference parameter, because we have some idea about this difference parameter in terms of effect size, say. So that's also why. So maybe we're just in perfect agreement here that this is a good thing to do.
The illustration you gave a different way of implementing equality.
Oh, you mean the different ways in which you can conceptualize the limiting process?
Yeah.
Like this or this?
Yes. I don't find that natural unless mu1 and mu2 are just scale parameters.
Right, right. No, but that's of course, that's one of the solutions or one of the arguments that people have brought forward is that this problem is just underspecified. And there are certain parameterizations that are more natural than others, and you should choose these. So that's true, but if you don't insert more information here, or if you don't have a good a priori reason to do it a certain way, but you just do this for convenience, then you can unrarely run into this this paradox, and many people still occasionally do this in literature, actually. I do at the same time. Yes.
Can I give a comment on the same topic?
Sure.
Because I agree with you that I'm not so worried about this problem because of the benefit that you want to talk about it too. But we developed the same kind of procedures for cross-classified data. And there, of course, people very often formulate the hypothesis in terms of odds ratios. And then you really have a choice. Do I expect two cell probabilities to be equal or cell probability or do I define it in terms of odds ratios?
Right.
And we run exactly into these kind of problems. That's for equality constraint models, the results are different.
Okay, well, I think with that, I think we'll conclude the model symposium section. So let's thank all the speakers, including the speakers.